Hello and welcome to More Interesting Maths. I'm David Myers with UTC South Durham. True to the name of the channel, this is More Interesting Mathematics. I'm going to show you a few elements of mathematics that inspired me to go and study maths at university and also afterwards just for curiosity. This is maths for maths' sake, for you at home, your curiosity and your entertainment. Generic introduction clip over, now let's do some maths. So today, while the sun is out and I am looking like an absolute ghost because the sun is blinding its way through my quote-unquote blinds, we're going to look at two of my favourite elements of number, that is palindromic numbers and mirror numbers. We love symmetry in mathematics and we can even get it from numbers. On screen you can see the word Hannah, and why is the word Hannah such a cool name, I think? Because you can reverse the whole thing, you can mirror it right down the middle or on the side, and you get Hannah out again. What do I mean by that? If I put my mirror line straight down here, flipped all the letters, so the first is the last, the second is the second last, and so on, you would still get Hannah again. But the thing is, you can do that with loads of different types of numbers as well. We could say that the number 2, let's put that somewhere more sensible. We could say that the number 2332 is a palindrome. We could say that the number 751157 is a palindrome. And what I really love about these certain forms of number is that actually these are all divisible by 11. Say for instance, if you were to do 2332 divided by 11, you would end up with 212. If you were to do 751157 divided by 11, then you would end up with the number, what's that when it's at home? Totally checking out my calculator at this point, 68,287. Now that's weird. And one of the first puzzles I was ever given when we started at university, it was only a 15-minute exercise, but it was the following statement. All 4-digit palindromes, such as 2332, are divisible by 11. I'm just going to call them P's here, are divisible by 11. But can you prove that? Is it even true? And of course the beauty of that was, how far can we take it? Try it out for yourself. Have a look, see if you can convince yourself and give a convincing argument as to why all 4-digit palindromes are divisible by 11. I won't go through that because I've got something way more exciting for you. After we were done looking at palindromes, these numbers that are symmetrical around the centre, we then started to look at the concept of mirror numbers. And mirror numbers seem fairly trivial. Say, for instance, 37, the mirror of 37 is 73. The mirror of 52 is 25, and so on. So that's all a mirror number is. You've reversed the digits. You may not necessarily have a palindrome, but all palindromes are mirrors just of themselves. Now, the thing is, what can we do with that? Well, say we could add them together. With if we added 37 and 73, we'd get 110. If we were to add 52 and 25, we'd get 77. So can all mirror numbers be divided by 11? We might be tempted to think, well, let's keep exploring it. What if we had, let's go with 77 and 77? Well, that obviously would, because we've got two multiples of 11 in there. What if we had 123 plus 321. Well, with that, we would end up with 666. I may have lost some viewers at this point, as I wouldn't get 666 at all. That's absolutely rubbish. We'd end up with 444. Is that divisible by 11? Well, actually, the answer is no, and you can try it for yourself. 11 will go into 44 with no remainder, so we can't divide that by 11. What we can do is set ourselves quite an interesting puzzle. Again, this is one that I gave out while I was doing a little bit of research, which looks at mirror numbers. So with the idea that we reverse numbers, can you find two mirror numbers whose product is 9,256? What do I mean by that? Product just means multiply. So let's say you were to start with the unlucky number 13. If you were to multiply 13 by its mirror, 31, you would end up with 403. So the first part of this puzzle for you is, can you find two mirror numbers whose product is equal to 9,256? Part B, if we took those same mirror numbers, you don't have to, you can have whatever you want. Can you find two mirror numbers whose sum, when you add them together, gives you 8,768? This one should take you a while. So, if you've been having a good go at this, chances are you've been sat there for half an hour struggling away trying to find some combination. Loads of you might have got really, really close with this. You might have got 9,274, I don't know. But you've been sat there racking your brains trying desperately to find anything. You'll have gone through any trick under the sun that you can think of. You'll have looked at different forms of multiplication. You'll have tried it with 2-digit numbers, 1-digit numbers. Can I cheat? Can I use 0 as the first number and do 906 times 6,090? Loads of different ideas. The trick to this, in order to find an elegant way, actually comes from something very related, but not the same. Most of us who've been in high school will remember prime factorization. And that's a big tool that we can use to help us figure this out. If we were to divide this by 2, we would end up with 4,628. If we keep going, we can divide this by 2 again fairly elegantly, 2,314. If we divide that by 2 again, that's going to be 1,157, I believe. And there's another factor of 2 in there. And then we have to get a bit stuck, and we must retreat back to our calculators to find out that this is, in fact, 13 times 89. And I'm very quickly going to check that, because I do not trust my mental arithmetic at all, but it turns out I got it right. So what we find is that the prime factors of 9,256, 3 lots of 2, aka 8, multiplied by 13, multiplied by 89. As in 9,256, its prime factorization, of which there is only one, is 2 cubed times 13 times 89. Now, I imagine most of us haven't done this at home. And you'd be right to think, well, what is the point? How on earth does this help us solve the puzzle? Because we're trying to find two mirror numbers. Well, actually, to begin with, what we can see is that if we multiplied 13 by 89, we'd come back to this 1157. And there's no way at all, that we can multiply that by 8. Well, we can multiply it by 8 to get 9256, but that's not going to be a mirror number. That's just 1,157 times 8. But what we can do is multiply either 13 or 89 by some combination of 2. So to begin with, I might want to multiply 89 by 2, and that would give me 178. Then we'd have to multiply 13 by 4, that'd give us 52. Again, we'd get the right result, but we don't have mirror numbers. So let's see what happens. We've got 3 lots of 2 to choose from. So if we multiply this by 2, then we have 26. We're still not looking at mirror numbers yet, but we wouldn't expect to. Let's try multiplying this by 2 again. So we've lost another 2. We've got 1 left so far. We have 52 times 89. And then we've got 1 lot of 2 left that we need to put in. So we had 3 lots left over here. Then we had 2 sets of 2 remaining, and now we've got 1 set of 2. So we can multiply one of these by 2, and we'll get the result that we're after. Well, if I multiply 52 by 2, then I get 104. Again, check it with your calculators. 104 times by 89, that will give us 9,256. Not mirror numbers. We could try going the other way. So we still had 52, and we multiply that by, what did I say it was? 160, 178. We'll get 9,256, but we don't have any mirror numbers. Now, this isn't a conclusive proof, but the short answer is no, you can't. There is no set of mirror numbers that when you multiply them will give you 9,256. And that, I argue, is the reason that you've been banging your head against the desk for however long, trying to find a combination of numbers that will do it. Loads of people will probably hate me now, and I'm about to lose all of my 16 subscribers or whatever. But actually, I think one of the beauties is sometimes maths will turn around and say, no, it can't be done. The solution is that there is no solution. So we had absolutely no luck with the finding the product. Actually, I think we had a lot of luck. I really quite enjoy sometimes being able to prove that there isn't a solution. I think that's still quite a nice solution in itself. And there's still a level of smugness to be gained from going, no, it can't be done, and I can prove it. There's something really nice about that, and that does form a huge branch of mathematics. But we move on to the sum, because surely that should be easier. Surely there should be loads of easy ways of adding a few numbers together to get the result. And again, loads of you will be sat there going, I managed to get 8,668, I managed to get 9,768. Loads of different ideas. And it was always close. I remember fondly while I was doing the research originally, there was one student who chucked his pen in the air. He was so excited. He turned around and said, yes, I found a mirror number. They will multiply to give 8,768. And there was quite a lot of choice language when he reread the question and found out that he was meant to be adding the numbers. And he went straight back to the drawing. No, I think he gave up on that one. He'd had enough by the time he was done. So, can we find a solution? And if not, can we prove that it doesn't work? Most of you, again, I've already lost probably 16 subscribers by this point, will be sat there thinking, I bet there isn't a solution. Yeah, probably right. But we still need to prove that that's the case. Well, let's have a look at how we can do that. What we can do to begin with is put it into some algebraic form. As in, we're going to call our two mirror numbers A, B, C, and D. Because we know that when we're adding the mirror numbers, we are adding D, C, B, A. Where that stands for the numbers that would go into that slot. If this A here was a 5, the number at the end in the mirror would have to be a 5, and so on. But actually that's not entirely true. That's not algebraically that accurate. What we're actually looking at is 1000A, because remember A is in the thousands column, plus 100B, plus 10C, and for completeness I'm going to call it 1D. Those of you who subscribe to the algebra channels and are looking in at those will know that you don't actually have to write 1D, but for completeness it works. And to that we are adding, well actually now there's just the 1A. And we can write it whichever way we want because we've specified that we have now 1,000 days and now there's the 1A from over here. We then only have 10 Bs plus 100 Cs and add into that 1,000 Ds. So again, let's use some elementary algebra. Let's see if we can rattle this up. There's actually 1,001 As, but there's also 1,001 Ds. And then there's 110 of the rest. 110 Bs, 110 Cs. I really like that because we can already see a fair bit of elegance going on. There's already something really quite pretty about what we can see here. We've got 1,001, lots of A plus D. And to that we also have 110 lots of B plus C. Why is that helpful to us? Why can we use that? Because actually, if we look very carefully at the result, we'll see that this last number, this 8, that has got to be formed by A and D. Notice that whatever B plus C is, whatever the two numbers that we choose in the middle, they have absolutely no effect whatsoever. They can't, because they've been multiplied by 10. They're going to have no effect on this final number. So we know that A plus D must equal 8. Well, that's okay. So we're thinking, right, there's a few possible combinations. I can think of a few numbers off the top of my head that'll give me 8 when I add them together. So how can we use that? We know we've already set the stage. We can create some numbers that will start with an 8 and end with an 8. That's fantastic. Because now we're getting one step closer. We know then that we could make B plus C equal to 6. Perfect. If B plus C is equal to 6, we have... Oh, wait a minute. We don't. If b plus c equals 6, then we run into a bit of an issue. Because if b plus c is equal to 6, then we would have 8... Let's leave that for a second. We'd have that as we wanted. And then we'd have a rogue 6 here. And we want more than that. We need it to be more. But does b plus c have to equal 6? What if we cheated a little bit? What if we cheated and made that 6 a 16? There's a few options for that. 9 and 7 will be the first one that pops into most people's heads, I suspect. So it is doable. What happens if we do that? Well, actually, that 16 then carries over and turns this into an 8, 7, 6, 8. Except it doesn't. Because sadly, that also becomes a 16 there, turning this into a 9,768. We were so close. So close and yet so far. Loads of you will be saying, aha, but David, what if I made the 8 and 18? Oh, I'm sorry, you couldn't have that either, because then you'd end up with a rogue 1 sat at the front here. So, again, it's not a complete proof. It's not a complete proof, but once again, the short answer is no. There are no two mirror numbers that exist that when you add them together will give you 8,768. That's a head-banging puzzle, and one that you can spend absolutely ages with, and in a lot of cases you can spend about as much time trying to prove that it will never ever work. For now though, I think that's a fairly succinct, it's not complete, but it's a fairly convincing argument that there are no two mirror numbers whose product will give you 9,256. There are no two mirror numbers that will give you 8,768 if you sum them. Hope you've enjoyed banging your head against the desk for the last half an hour, but I hope you've enjoyed more this fairly decent, I think, argument for these two puzzles. And that is it for this video, ladies and gentlemen. Thank you so much for watching. If you think it helped you out with your maths revision at home, then please click subscribe to get notifications on future videos. Share it with a friend if you think it will help them as well. There is a PayPal account, but please don't feel obligated to do that. 10 or 12 pence if you think that it's worth it for you at home and you liked the video and the content that I've put out. Failing that, thank you so much to Dr. Frost Maths for the slides, for UTC South Durham for inspiring these videos, and most importantly to you at home for watching. I'm David Myers. Take care.